So I'm William Guss. I'm from an organization on campus called Machine Learning at Berkeley. We're kind of an undergraduate, graduate organization that does a lot of research independent of some of the labs here. And today I want to talk to you guys about a little bit of deep learning theory. So upfront warning, it will get a little bit mathy, but I'll try and give you some intuitions for what I'm going to talk about. But the core theme of this talk is really about the expressivity of certain neural networks. In deep learning theory, like kind of the state of the art to ask, or like one of the most pertinent questions is, why are these deep models more expressive than their predecessors? And that's a really interesting question, and you kind of can get results about activation functions and different sorts of weight distributions that you initialize with. But I want to ask a different question. I want to ask why convolutions are so expressive, right? A lot of the time when you ask people about this, they'll give you the standard response is we have some notion of pixel locality. Pixels are close. We want things to be translation invariant. And this is a reasonable answer. But I want to do something a little bit more rigorous. I want to talk about how the topology of the data influences the topology of the neural network. What I mean by topology is like which neurons are connected to which that best expresses functions on that data. And in this sense, we have to kind of operationalize what it means for this images to have pixel locality. So the way to formally state this question is it's going to be a little bit mathematical, but really you start with some data distribution, right? You have data, and it lives in some space latently, and we like to assume that it's on some manifold, which is just a really high-dimensional shape. And then we want to ask the following question, right? If I have a neural network without layers, parameterized by some weight matrices, and I have a set of weight matrices, given the topology of the data, and what I mean by topology is there's certain invariants, like the number of holes in the data. I can even talk about differential properties, like the curvature of the data. But given that all my data are on this distribution, I want to ask what sort of weight matrices, what set of weights yield the most expressive neural network? And when I mean expressive, choose any given expressivity measure. It might be Rademacher complexity or whatever you want, but the general question is if I have some expressivity measure, how can I find the neural network weights that are really going to be most expressive? So the starting point, like I said earlier, is convolutions, right? And we're trying to look for a rigorous way to define what it means to have pixel locality. And the best way I thought about doing this is, well, instead of assuming that these images are just this, R times L times width times, the number of channels tensor, why don't we think about images as functions, right? We're sampling basically height values from some sort of piecewise smooth function. And you can do this on a variety of different natural images, and you kind of get the same result. There's this piecewise smooth property up to something called countability. And this is actually really nice. It rigorizes the notion of having pixels close to one another. It rigorizes the notion of having colors that move smoothly into one another. And it actually lets us talk about topological properties of the image manifold. So the only assumption I'm really going to make during this talk is that you can either have images as vectors and sample with different resolutions, but what really is happening is all images are some manifold in the space of surfaces. And surfaces in this case are just functions on R2. So they're just really all images, natural images, are a collection of height value surfaces. And if you do this, you actually rigorize what it means to have pixel locality, and you want to start asking questions, okay, now what neural network weights are most efficient? What are most expressive on this manifold, okay? The only problem is when we turn images into continuous functions into smooth surfaces, we don't really have neural networks that deal with that from a theoretical perspective, right? There's uncountably many height values, and how would you kind of grasp with that? Well, it's actually kind of simple when you break it down. So the best way to describe this generalization we're about to make from neural networks that take vectors to neural networks that take functions is kind of thinking about 1D signals. So let's start with a signal C. This is the ground truth image, right? And for each pixel index, we might go to the right on this graph. And when you have a really low resolution sample of that, you will have like this piecewise step function. So let's say this is a 1D image, and I have a vector of 3 pixels, right? 1, 2, 3, and they have a certain value. As I increase the resolution, I'm also increasing how close I'm getting to this approximation. And you imagine when you take photos with high resolution, you're going to get this nice result, this notion of locality and local linearity. What happens to the neural network as you do this is you increase the number of weights. An increasing number of weights is kind of bad because you run into saturation problems, right? If I have infinitely many weights, uncountably many weights, I'm not going to have any neural network whose net input to a next layer's neuron is going to actually not have non-infinite values. So the way you deal with this is obviously you increase the resolution of your input vector. Imagine you get higher and higher resolution cameras. And then as you're doing this, you get a bigger and bigger weight matrix, but you discount each sample by the amount you've scaled up. Because there's this notion that two pixels close to each other aren't going to have that much new information. But as you do this, you get this basically infinite neural network. And what happens to the weight matrix is instead of having, this is a height value plot of a weight matrix, for example. Instead of having these discrete little step pieces, you get this smooth surface. One of the first results of this paper I'm going to talk about later is that you actually can prove that this thing ends up being smooth for images. But from the mathematical standpoint, what's actually happening here? Well, you have your standard neural network where you have some input vector x, some weight matrix you multiply by, and a nonlinearity. What you do is you just do the relaxation I told you about. So you go from an input vector x to some smooth signal c. So this is your weight surface. This is your initial image that you're putting in. And instead of doing some weight matrix multiplication, you actually just integrate along it. You're not summing, you're integrating along slices of this image. And so what this does is it generalizes neural networks, and we'll call this an operator neural network, to uncountably many neurons. And now we can actually start talking about what might be interesting about the weights. So instead of talking about classes of weight matrices that are most expressive, we want to talk about classes of weight surfaces that are most expressive. Before we get into that, let's look at what convolutions look like in this case, right? So if you think of a standard convolution, it's really easy to generalize to integration forms. You have your input image here, and you have some filter, and you're dragging it at a rate c across the image. What your weight surface looks like, if you were to take some weight matrix, it would look exactly like this nice, smooth ridge across. But what's interesting is if you make smoothness assumptions on the manifold of all images, right? You say this is a very smooth manifold, and in fact, it is a subset of function space. You can make a really interesting connection. You can show that all convolutional neural networks have basically these weight surfaces and weight matrices in the discrete case that are solutions to the wave equation. So this wave equation, if you're not familiar with it, is kind of this ubiquitous differential equation, dynamical system from physics. It talks about how waves propagate through space and kind of describes certain solutions in Fourier space. But this is an interesting connection you can make, and you can prove directly with this framework. And the sketch proof is, okay, well, convolutional filters look something like, you filter and you drag it along the image, along some index, and the solutions of the wave equation look the same. It almost seems tautological, but you need this rigorous framework to actually prove it, this rigorous extension to infinite dimensional space. So that connection's pretty interesting, but it kind of leads you to more questions, right? We made one assumption at the beginning of this talk, that images are just smooth surfaces. But what if we start trying to ask harder questions, right? There's these things in algebraic topology, which is the study of topology in its discrete form, almost, that talk about how many holes are in the group, how many cycles are in the group. So if you think about a torus, which is just this donut, you can ask how many holes are in a donut, and you get the answer 2. You have this homology group that describes this. The question is, if our data has certain topological properties, what do these weight surfaces look like? So this generalization right now gives you access to those kind of questions. It gives you access to differential questions, right? The next thing you might ask is, well, we just saw that the wave equation is really connected to convolutional neural networks, but what about if I have any smooth manifold for data, right? I think of MNIST, for example. I have any smooth manifold, I make some restrictions. Are the most expressive set of weight surfaces always solutions to dynamical systems? Why is the wave equation so special? Can we come up with a notion of all of these weight matrices being smooth? So this is an interesting question you might want to ask, but more pertinent and more experimental is, can we do better than convolutions? So if I go back to the slide, the way you learn convolutional neural networks is you come up with a filter, right? In the discrete case, it might be like an m by n filter, but if we're thinking about 1D convolutions, you come up with a filter, and you just gradient descend on the height values of this filter, and then you drag that across your image. Is that parameterization really rich, right? Because one thing you can show is that if you're talking about smooth images, your convolution filter might do well to be smooth itself. Why would I choose different height values that aren't related on this filter? So the question is, can we come up with a smarter parameterization? And one of the results that you can get is, well, we have the wave equation. Let's see if there's more general solutions. And right out of this, I'm introducing something called wave layers. It's just a different parameterization for this notion. So instead of parameterizing a filter by its height values, right, and gradient descending on that, what if we just look at this weight surface that we have come up with? We abstract it out. And we say, I don't want to parameterize by the height values. I don't care what happens at each pixel. I don't care about the resolution. I care about globally what's happening. And parameterize your weight surface, the thing you integrate across, using the sum of cosines. So you basically build up a bunch of waves, you point them in a certain direction, you give them a certain phase offset, so moving them left or right, and you scale them. If these are your only parameters, can you do better than convolutions, right? So this is kind of abstract right now, but what you would do to make a neural network that does this is you come up with this weight surface, right? And then you, let's say, have an input of resolution 100. So you sample this at every 100 steps in both directions. And what you get is a normal discrete neural network who's parameterized not by the height values of a weight matrix, but by these maybe 6 or 7 parameters. And when you do this, you actually get something really nice in practice. So before we get into it, this is just kind of a comparison of what these things look like in practice. This isn't just, oh, I'm doing infinite dimensional neural networks, there's no application here. This is literally taken from real experiments. So for the same experiment I'll describe in a minute, you do a fully connected layer, you get a weight matrix that looks like this. And the height values are kind of really decorrelated and nasty. If you do the same thing with a convolution, you get something like this, and this is all nice. And this is just one filter, right? When you do an experiment like this that I'm about to talk about, you have something like 30, 60, 70 filters, several layers, et cetera. But with a wave layer, you just need one quote-unquote filter and these 6 parameters. And to talk about what this experiment really is, I'm just going to show you the very beginning of training. This is a very toy task, but you're given some input signal. And this is just one thing from the test set, but it's maybe a sum of different bump functions. And your goal is to take that function, that red signal, and square it. It's pretty hard to see on the slide, but doing the square, especially when you have multiple bump functions, is a nonlinear operation. It's not very clear-cut. When you train a convolutional neural network to do this, it runs into issues of how big is the filter, how well can I approximate this nonlinear operation. But when you use a wave layer, you can get away with a drastic reduction of parameters. You don't care about the resolution. You could have a signal of 100,000. You just need to sample this smooth weight kernel, and you actually can get this thing to learn a lot quicker. So like with a task this particular task, it was something like 900 different filters just for overkill purposes on a convolution, and you can reduce that down to like 30 filters. But with a wave layer, you only need something like 16 parameters to do this task, right? But each of these filters for a convolution is a bunch of parameters because you're parameterizing each height value. So the question is, can we do better? And what you can show is this formulation, the sum of sines, is actually the most expressive solution to the wave equation in this context. So these experimental results are nice, and what we wanted to do is actually kind of abstract this into a general paradigm for deep learning theory, right? Why just stop at analyzing images? But generally, we want to talk about all topological data spaces. So this definition is a little tedious, and I'll just jump into some examples and then come back to it. But what we did, if you remember, is we started with a discrete neural network. We made some assumptions about where the data lives, what kind of manifold or shape it lived on, and then we extended a neural network to handle that kind of data. We needed a neural network that can handle functions. So to make this paradigm a little bit more general, what we do is we say, given any sort of vector space, infinite dimensional, whatever you want, we want to build up a set of different neural network paradigms that allow you to compute in that space and then do analysis in that space. So with deep function machines, we build just basically a generalization that says, OK, I can start with a function space, a set of continuous functions, and I can go to another function space to another function space. This was this operator neural network we just talked about. I can start with a function space and go to a real valued vector space. I can go to another continuous vector space. But the notion is we want to do topological data analysis, and maybe sticking with real valued vector spaces, finite dimensional vector spaces, isn't enough. So I'm going to skip over this stuff because it's pretty mathy. But the general framework is you start with a data manifold, and I want people to start thinking this way because we don't have answers about topology in deep learning. But you start with some data manifold, and you say, where does this thing best live? Images clearly didn't live in this finite dimensional vector space. They lived in function space. But start with some manifold, do analysis on it. Then you find a type of layer that can eat those data points. So in this case, functions were eaten by operator neural networks. But there's a whole class of neural networks proposed in this paper that let you analyze different spaces. When you analyze the weight matrix, what you can do is then find the most expressive class of weights. Like I said, wave layers were an example of an expressive class. And then all you have to do is sample it. So like I said, you build that weight matrix and you sample at different heights. But this is a new way of thinking about parameterizing neural networks. Why just stop at choosing height values, but think really carefully about what is most expressive, and use topology as your basis. This is what I want people to start thinking about. And if you want to read more about some of the proofs we give in the paper, as well as all of these different quote-unquote deep function machines we come up with, it's all on arXiv, and you feel free to check it out. Thanks. That's all I have.